Let's record this one too. Okay, no questions? Let's start. So first, we are going to study set theories, set theory, sets and mappings. Okay, so I think you already know what sets are. Okay, a collection or assembly of objects. Collection or assembly of objects is called a set. And those objects must be distinguishable. Okay, and each object is said to be an element of the set. That's the definition. And I skipped the exercise, and here are some here is one example. Let it be a set that has 1, 2, 3, 4 as elements. Okay, so this set is written like this one. Oh, you can write, this is not a set actually, but this has two elements, the same elements here, 1 and 1, 2 and 2, but these are not distinguishable, so we can just erase, get rid of these elements and get the same set like this one. And this is 1, 2, 3, 4, but this is 2, 1, 3, 4. The order is different, but it's still the same set. We don't care about the order when we consider a set. Okay. Here's the next definition. Let A be a set if A consists of a finite number of elements. Finite number of elements. Let's say A1, A2 up to AN. So we can write like this one. A1 to AN. Just enumerate all the elements here inside these braces. In this case, A is said to be a finite set of cardinality n. Cardinality means the number of elements in a set. And this cardinality is written like this one. So just like absolute value of set. And if A does not have a finite number of elements, then A is called an infinite set and said to have infinite cardinality. Okay. And if the set has no elements at all, then it is called the empty set. Or maybe sometimes it may be called a null set, but maybe we shouldn't use this one because it has another meaning in another field of mathematics. And the empty set is denoted by this 0 and this line. Okay, and of course the cardinality of the empty set is 0. Okay, here are examples. The set of all unicorns is empty because there are no such thing as unicorns. Okay, and the set of all persons living on the moon in 2020 is empty because no one is living in the moon right now. And the cardinality of this set is 4 because there are 4 elements. And likewise, this is 5. Okay, should be easy. And just we move on as fast as we can for this chapter because I think you already know all of this. Okay, let P be some property. Property is something like a color is in the rainbow. Okay, the set of elements, each of which has the property P, is written as this. Okay, so this means we can define a set by specifying a property. Okay, so this is a set, the set of all x such that x has the property P. Okay. Maybe this is too abstract, so let's give an example. Let A be a set of the squares of all strictly positive integers. Okay, so that means A is a set of numbers such that 1, 4, 9, and so on. Because 1 is the square of 1, 4 is the square of 2, 9 is the square of 3, and so on. Okay, but this notion is ambiguous because this dot dot dot, what does it mean? This can be maybe 16, but why not 10 or 11 or whatever? This is ambiguous. So to be more precise, we can write like this. So A is a set of x such that x is n squared for n 1, 2, 3, and so on. Okay, so this is a little bit more precise because it says elements of A, this set, must be a square of some number. Okay, but in this case, 1, 2, dot, 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 what does it mean? Does it that the number next to 2 is 3 or 5 or 112? Whatever. It's not precise enough. So, to make it more precise, we can write like this one. So A is a set of x such that x is the square of some number where n is a natural number. Okay, so this is perfectly precise. Okay, because natural number means a numbers from 1, 2, 3, and so on. So all natural numbers. Just by saying the natural number, a natural number, we know that this is some of these numbers. Okay, so this defines the set A here. And these are the properties of x. Okay? And n is a natural number and n squared is x. Okay. Next. Next example. The set of x such that x is less than 0 and x is greater than 1. So this is a perfect example of a set. But this set is empty because there are no numbers such that less than 0 and greater than 1 at the same time, right? So this is empty. This is empty. And this set also, set of all x such that x squared is 3, where x is an integer, is empty, right? Because no integer exists such that if squared, which is 3, because if x squared is 3, x must be positive or negative square root of 3, which is not integer. So this is empty. Okay? Okay, next definition. Let x be a set and let x be an element of A. An element. If x is an element of A, we write like this. So you know this already. And if x is not an element of A, we write like this. It's not an element. So here example. A is an element of this set. B is not an element of this. Unless, of course, you have an equation like B is equal to 2, for example. if we know this, then B is an element of this, but unless we know this, B is not an element. Okay? And check these ones too. Okay. Next. If a set A is, not if, a set A is said to be a subset of a set B if every element of A is also an element of B. Okay? So in this case, we write this. A is a subset of B. Okay, this, instead of this, we may write like this. Some people write like this. Actually, I prefer this notation than this notation. Okay. So this this bar implies equality. Okay. So A can some elements of B may not belong to A, but if all elements of B belong to A, then these two sets are equal, which we will study next. And if A is not a subset of B, we write like this. Okay. And if A is a subset of B and B is a subset of A, okay, so these two sets are subsets of each other, then sets A and B are said to be equal. And we write A is equal to B. Okay? So this equal sign is conceptually different from the equal sign between numbers. Okay? But we still use the same notation, equal. Equal. Okay? Okay, let's review this definition again. So if every element of A is also an element of B, then A is a subset of B. So that means all elements of A, for all elements of A, X also belongs to B. Okay, so this means this. Okay, and this means for all elements of A, X belongs to B.